Thanks for the introduction. Can you hear me? No? Now, yes, okay. Thanks for the introduction. First of all, I would like to thank the local committee for the invitation to take part of this exciting workshop. It's for me a real pleasure to be with you. I want to say that although I held a BSc on theoretical physics, all my research career has been related to classical machine learning. But 3 years ago, approximately, I started to read some papers from, that mostly were written by people who are here in this audience. So it's for me a real pleasure to have the opportunity to share this time with you today and in this workshop. And then I realized that was a good opportunity for me to put together my two passions, that was originally physics, but for my research career in the case of classical machine learning. So I've been doing some work in the last few years, trying to mix both fields and trying to squish most of the fruit from both of them. So, okay, this is the outline of the presentation. I want to say that my original presentation was a bit different, was short of trying to talk about both approaches, both quantum and classical at the same time. But after these 2 first days of workshop and also having a look at the presentations that will be given in the next 2 days as well, I've tried to modify it a bit in order to produce something that can be complementary to your presentation. So the presentation will then be somewhat biased to classical machine learning, that it's not as usually tackled in your presentations. And then I will, if I have time, I will give some clues about the relationship with quantum approaches. So first of all, why machine learning and why data analysis, all these topics that we are talking usually in the last years. It's true that now we are just watching TV news and we hear about machine learning and we hear about data analysis, big data, many terms that seem to be very popular. Even my friends, my personal friends that work in completely different fields, after 20 years trying to explain what I was doing, now I say, okay, the other day I was watching TV news, something about big data. This is what you are doing, right? Okay, I was trying to explain that for 20 years, and now you are asking me what I was doing. So now it's becoming more and more popular. And why is it so popular? Basically because in the last decade, let's say, more and more data is being collected. So we have huge databases. And companies, public entities as well, need to do something with this data. And as we will see later, machine learning is one of maybe the most adequate ways to extract information to create knowledge, real knowledge from this raw data. And it's not something, punctual, it's something that will even increase in years to come, because, for instance, social networks that now are extremely popular are just acquiring data from all of us continuously, non-stop. So we need to really develop tools that create this knowledge and help in doing things much better for users and also for companies. This is just, I was just learn a bit, and I just selected a couple of snapshots about this trend that will continue increasing in years to come. This is just some estimations about how things might be in the next few years, or the growth in data science jobs in the last 5 years. So as I said, the reason for this boost of machine learning is actually related to data, to the need of really carrying out an interesting and a useful data analysis. And to do that is not something exclusive to work with machine learning. There are other techniques, many techniques that come from the field of statistics as well. But machine learning is something that makes a difference. Why does it make a difference? Because it's based on learning algorithms that, as you know, the goal is, to map some input space onto an output space. And by doing that, we create knowledge. We extract the relationships that might be telling us what's the problem we want to solve, what's the problem about. As I said, it's closely related to data mining, to computational intelligence, and originally it's designed to solve different kinds of problems. Problems that we've seen in the previous presentations here in the workshops, presented by some of you, like classification problems that I've seen a few works of you talking about that. Also prediction or modeling problems in which the goal is no longer just to classify between 2 or 3 different classes, but to know a future value of something. For instance, something that I heard yesterday, that predicting the value of a stock market, just to give you an example. And also something very interesting, very important for you, I think, which is planning. I've seen that some of you are working on reinforcement learning algorithms to design quantum experiments. And reinforcement learning actually what produces is a sequence of actions to achieve a given goal. And this is what we call planning problems, because the idea is to develop a policy, to develop a plan of what I should do in order to achieve a particular goal. So some of the most hot topics on machine learning, classical machine learning, in the last few years include deep learning, after learning, and of course big data. Also, reinforcement learning is quite relevant, but as it's a topic that has already been explained in previous presentations, I've decided to focus today on deep learning, active learning, and big data to give you a global picture of what we are talking about. So let's start by the last one, by big data, because again, as I said, everyone is talking about big data, about machine learning, but what is exactly big data? Actually, to fulfill what we understand by big data, we should fulfill, or we should accomplish some requirements. These requirements are usually called the V's of big data. We should have different V's. The most important and most relevant V is volume. Big data appeared because we had huge databases. We had many data samples, and we should develop new tools to extract information from that. So volume is the first one. For instance, this is just an estimation of, as I said before, how things are changing in order to acquire data. 90% of the data ever created was created in the past 2 years. It's an amazing claim. Also velocity. It's not just a question of extracting knowledge, but we want to do this analysis, if possible, online. If we, for instance, we own a very large company and we want to recommend our users what they should do, we should do it, in online, or at least as fast as possible. And we are not interested in carrying out an analysis that takes months, and then 3 months later say your user, oh, you should have done that, but 3 months ago, sorry. No, we need this velocity in real life. Also variety, which implies this is very important, a very important view of big data as well. And when we talk about big data, it's not just a question of having a large database, but usually different types of data should be playing different roles there, like having, I don't know, text, images, numerical values, different kind of information. Two more V's are veracity, which is the ABC of veracity, is try to deal with some problems that appear in data analysis, like artifacts, bias, or chance variation. And also variability, which is not exactly the same as variety. As I explained before, in variety, I meant having different kinds of data. And in the case of variability, what I mean is that exactly the same thing may have completely different meanings in different contexts. For instance, if we think of social networks, maybe a tweet written by me maybe today, I tweet that I'm giving a talk here, and maybe this talk has nothing to do with another tweet from a different guy who's talking about a completely different thing. So it's important to analyze the context of the information, and this is also a quite relevant topic in big data. And some additional aspects are visualization. I mean, when we are dealing with data analysis and with data sets that are very complicated, visualization plays a very relevant role because, one picture, as it said, is worth 1,000 words, and maybe with just one visualization, we can acquire much more information than, in a very complicated data set or in a very complicated matrix of points that it's much more difficult to understand for experts of other fields. And finally, money. Money is, in our society, is important, so most of the companies involved in that, at the end of the day, what they want to do is to make more money from using their data. Said that, that the big data is very popular and so on, it's not everything. Everyone, as I said, talks about big data, but actually many cases, or in most of the occasions, what we have when we try to do data analysis is that we are not in the framework of big data. We don't have different or very large database with different variables of different nature, and then unstructured data. But maybe, oftentimes, it's not that complicated. So in fact, it's now very trendy in the field of classical machine learning to talk about small data. So now it's one of the new trends and the topics that maybe in a couple of years you will hear a lot. In the case of small data, we don't have large databases, but small ones. And the thing is that this is not necessarily bad. In principle, as a data scientist, my view is that as much as possible, always, I want as much data as possible, as much information as possible. But the thing is that when we have so much information and when we want to apply big data tools to these complicated data sets, it's not easy to extract information. We can't think of a very complicated data set and then suddenly trying to apply a very sophisticated tool to extract information. It doesn't work that way. If we have a very complicated data set, if we have very strange interactions there, then the only thing we can do is to do very simple stuff. We use linear models, extract very basic information. But when we have small data, we have much more manageable data sets, and then we can actually apply much more sophisticated tools. So it's not necessarily bad to have small data sets. And sometimes the problem is even that you, for different reasons, in a particular problem, we don't have really enough data, or we don't have as much data as we would like to have. For instance, in the case, an example might be the case of genetic analysis. This is very common now to try to extract information from genomics. And this is quite expensive. I mean, this kind of analysis are very, very expensive. And there are many features that are associated with that analysis. So in that case, we usually are working with just a few samples and trying to extract as much information as possible from these samples, maybe applying some tools or some tricks in order to create more data or to simulate more data and have something that can really solve the problem. And another kind of data that is very popular now, and it's not big data, it can be in the future, but it's not yet big data, is the so-called dark data, which is like the dark matter in data science. The thing is that, as I said, we are just acquiring data continuously, and but we don't use it, actually. I mean, the estimation is that around 90% of the data that is acquired in a daily basis by companies or by public entities has never been used whatsoever. Will be ever used in the future at some point? We don't know. I hope so. I hope that we can we can come up with solutions to really squeeze our data sets 100% or near 100%, but it's not the current situation at all. So this is something important to take into account. In fact, looking at this dark data, if at some point in the future we are able to really deal with this dark data, we will mostly be within the framework of big data, because most of the data that is not used right now really fulfill the previous V's that I mentioned when I was talking about big data. So moving to more machine learning stuff, maybe, or maybe not, I mean, the most popular topic now is something that has already been mentioned here in previous presentations, is deep learning. I mean, with deep learning, as Joy said yesterday, we now can solve problems that were considered completely impossible to be solved some years ago, and this has changed things a lot in the field of machine learning, and is one of the main reasons why machine learning is so popular right now, because of deep learning. Also, as Sergio said yesterday, it's not as new as one may think. We've been basically hearing about deep learning in the last, let's say, 5-6 years, something like that. But from the beginning of neural networks, it was something that people knew, or it seemed sensible to think that if we have a neural network with connections, then if we have a deeper and deeper neural network with more connections, we should be able to solve problems that were more complicated. But the thing is that we didn't have either the computing resources nor the mathematical or the tricks needed to train these neural networks. But things changed a few years ago, and because of that, we started to solve problems that were, as I said, impossible. And it's something that also, as it's been previously mentioned in yesterday, is something that we really have even in our smartphones. We have deep learning tools implemented, for instance, in our face recognition tools, and also in our store of pictures. We have this really working, and this really being implemented today. There are like 3 main implementations of deep learning autoencoders. and deep belief networks. Deep belief networks is like a concatenation of the restricted Boltzmann machines that were explained yesterday. So I will skip this part because it's already been mentioned in previous presentations here. But the idea is the same. It's like an unsupervised learning in which we carry out some feature extraction. Then the start of deep learning is convolutional neural networks because, as we will see a bit later, they solve problems about image classification that are very complicated and were impossible, not very complicated, just 5 years ago or 6 years ago. Also, maybe not that very popular, but widely applied are recurrent neural networks. For instance, in case of speech recognition and natural language processing is a very useful tool, and it's, as I said, widely applied in real life. And now the topic is this. I mean, the last 2 years, everyone in deep learning is very, very, very interested in these generative adversarial networks. These kind of networks produce data. I mean, the thing I will explain not in detail, but I will explain the foundations in just 5 slides, something like that. I mean, the idea is that we will be able not only to solve the problems, but also to produce the samples needed to solve the problem, which is pretty interesting. So let's start with autoencoders. In the case of autoencoders, the idea is very basic. We have, in principle, high dimensional data space. In this case, when I say high, it's just 4, but might be much higher. And then we try to find a lower dimensionality representation of this original data space, with the idea, of course, that if we use this encoded data, we will be able to decode this data by applying some function or some combination of parameters. In principle, this will correspond with a linear autoencoder in which the values of the encoder are just a linear combination of the original data, and then the values of the decoder are a linear combination of the already coded values. This is the most simple situation. We can we can work with nonlinear autoencoders. We can even work with deep autoencoders. That means that each one of these neurons or cells or whatever you want to call that can be a deep neural network. I mean, we can even create an autoencoder that is a deep neural network in itself. But I mean, to explain the main thing, we can have the idea of a linear autoencoder, and it works exactly the same to understand the topic and the concept. Why are autoencoders so important? They are crucial, or they've been crucial for the success of deep learning. When I said that some years ago we weren't able to solve problems that we can solve now even with a smartphone, it was for 2 main reasons. One was, of course, because we didn't have enough computational resources. That's true. But this is not the only thing. The thing that was that even with intensive computing, it wasn't possible, or it wasn't easy to solve complicated problems like recognizing a face, something trivial for us as human beings, but extremely difficult for a machine. And the autoencoders allowed to pre-train deep neural networks. So if we have a deep neural network with many, many connections, by means of autoencoders, we can initialize these connections, the values of these connections, with smart values. I mean, when I say smart values, is that maybe instead of needing 1,000 iterations to converge to an optimal value, maybe with just a few iterations, we can do that. So this was the success of autoencoders in my field. So, I mean, there are like two aspects associated with autoencoders. First, they can create high-level features. They can compress data, but at the same time, they were very, very relevant in the, in the success of deep learning in general, because it helped other deep neural architectures to be developed. The way, without going into the details, but the way of pre-training with autoencoders is that if we have something like that, is not very deep, but to understand the idea, we have two hidden layers. The idea is that the first hidden layer is trained by means of an autoencoder, in which we have here the encoder part and here the decoder part. We discard the decoder part, and we keep these values and incorporate them as the initial values of the network, and the same for the next layer. So this is the way why it worked so well. And a particular topic in which I've been lately involved, collaborating here with my dear friends from Bilbao, it's been in a topic related to quantum autoencoders. I planned to mention a bit about quantum autoencoders at the end of the presentation, but also as talking about analyzing the presentations that will be given in the next 2 days. Lucas Lamata will tell something about that on Friday, so that allows me to skip this part and have time to finish my presentation. I don't plan to give too many details about convolutional neural networks, because they were explained yesterday as well. But basically, they are like the pop star of deep learning, because these were the models that allowed real image classification. And why or where was the point to really achieve that goal? The thing was that, convolutional neural networks are a deep architecture with many connections there, some of them that were already explained yesterday. But one of the most important things here is that they make use of weight sharing. Weight sharing means that, for instance, all the orange arrows here have the same value, the same for the purple ones, the blue ones, the green ones. So we have what we call weight sharing. When we have weight sharing, it means that first, we have the same values of weights. So in terms of computational resources, it's much more convenient, because we don't need to train a very high number of parameters. This is the first thing to take into account. And the second one is that it allows translational invariance. This is the key aspect for these networks to be successfully applied to image classification or to image recognition. Because a very typical problem when we try to use machines to, for instance, to recognize faces was that if I take a picture of myself and I was just in the left side of the picture, and then I take exactly the same picture, but I'm in the right side, for a computer it was very difficult to really understand that I was the same person, because it was like completely different information what was there in the picture. By means of this translational invariance, these kind of models know that an object that is in one part of the picture, if they move to other parts of the picture, the information is there, and it's exactly the same information. This is why they were so successfully applied to image recognition. And as I said, something maybe not that popular, but widely applied in many fields is recurrent neural networks. It's very interesting because it can incorporate, because it can incorporate the prediction of sequence of variable length. For instance, thinking of a stock market, we can use all the historic information of a data set to produce the output. It's not just a question of use exactly the same temporal window. We can use different sizes, and this is very useful to really produce this kind of outputs in this kind of problems. As you can see, also weight sharing plays a relevant role here, but we are no longer interested in translational invariance because, for instance, in terms of prediction, if I'm thinking, I'm not an expert on economy, but it makes sense that to predict the next value of a stock market, the current value will be much more relevant than the value that was measured 3 years ago. So we are not interested in this translational invariance in this case. There are, as I say that I need a bit more time, I'm going to speed up a bit. There are some variations of recurrent neural networks. Maybe the most popular one is the LSTM, in which the idea is to use basically the same recurrent neural network as before, but we allow like alternative paths. By these alternative paths, the idea is that when we do the backpropagation that was already explained in previous presentations, in a recurrent neural network, we have so many steps, but maybe with this backpropagation, if we have a very low value of the gradient, the value is vanishing, vanishing, and vanishing, and at some point it disappears. So in case it disappears with LSTM, we have like alternative values to perform this backpropagation in order to really have training all the time. And the most important topic on recurrent neural networks right now is what we call the attention model. Everyone who works on recurrent neural networks now is paying a lot of attention to that, because the idea is like developing a recurrent neural network, but instead of giving the same relevance to everything, we can pay special attention to some aspects of the prediction. For instance, if you know that some variables might be more relevant than others in a particular problem, or you know that, I don't know, in a medical problem, a temporal window of 3 months is needed to perform a given prediction in the future, then we can pay special attention to these aspects by means of special connections. As I said, it plays a very relevant role in natural language processing, which is one of the main issues in data analysis, in part due to the fact of social networks, and in many different aspects, like parsing and part of speech or name entity recognition. And finally, regarding the deep learning, generative adversarial networks, as I said, is one of the most popular topics right now. In this case, we have a neural architecture with 2 networks that compete with each other. One is the generator, and the other is the discriminator. And they are like playing one against the other. The generator produces samples that, in principle, they are supposed to be part of the training set. And the idea is that the generator should make the discriminator believe that the sample belongs to the training set, even if it's not a real sample, but should be similar enough to make the discriminator believe that. And at the same time, the discriminator is like the referee, and it should say whether the sample is good enough to belong to the training set or not. The usefulness of that is that by using this kind of models, by using GAN, we don't need huge data sets to produce something, but just with few samples and a good generator, we can produce an informative data set. So it's a cheap and smart way of producing data. This is just an example. For instance, in the case of producing images, we have here the generator that produce fake images that go to the discriminator, and also we have here real images. And the discriminator should predict whether the images are real or not. In terms of implementation, they are usually implemented by means of convolutional neural networks. The discriminator is a normal one, a standard one, and the generator an inverse one. Um, with just finishing off the part of classical machine learning, I would like to talk about active learning. My feeling is that active learning might be one of the most relevant contributions for you in terms of quantum experimentation. It's something that has not yet been developed as in the case of reinforcement learning, that I've seen some works in this workshop and in previous papers talking about the use of reinforcement learning, but active learning can even play an addition, or can give an additional value to this optimal quantum experimentation. The idea of the active learning in the classical realm is that we usually have data, but sometimes labeling the data is expensive, either because we need a guy like this labeling, and we have to pay him, pay her, or we need I don't know, something very sophisticated to really analyze a particular image or a particular text, and this is expensive. So because of that, we usually work with semi-supervised learning, in which we have part of the training set that is labeled and part of the training set that is not. And active learning plays a very relevant role there, because it not only allows to work with both labeled and unlabeled data sets, but it says, okay, you should label this particular sample, and the final, or the idea is that at the end of the day, we will have just a reduced set of labeled data sets, and these reduced data sets will be the most informative one that is possible in my data set. So I think that in the case of quantum experimentation, that might be extremely useful, because you don't need to measure, you don't need to destroy your superposition states, or at least some of them, but just analyze which kind of measures you should take. I mean, in order to take every possible measure, just the minimum possible number of them. So I think it will be extremely useful for you. This is just an example. Imagine a very simple classification problem in which we have the green class and the red class, and we say, I think that here there are like 400 samples, if I remember well. Say, okay, I'm going to label just 10% of them, 30 samples. If we do it randomly, we have this border separation of the two classes, which is not very bad because the problem is very simple, but it's not good either. And if we use active learning, as you can see, what we label is the samples that are most informative to really solve the problem. Without going into details, because as I was afraid I'm running out of time, basically the idea is to label the samples for which the model is most uncertain about the possible output. This is one of the possible approaches. There are many. This is the most popular one. And another popular approach is what is called query by committee. And in this case, the idea is that we have different models, and we analyze the prediction of the different models. And we label the sample for which there is most disagreement between among the different models. As I said, it can be a key solution for quantum experimentation. This is my feeling, and is one of the, I think, is one of the fields that should need special attention in the next few years. This is a video that I prepared. As I don't have too much time, I will spend a lot of time in the video, but I want just to show you that, as it was said yesterday by Jody, let me see, it works, okay. Machine learning is already working, and this is just an example, I mean, a fun one, about something that is, it doesn't work well, okay.
In today's hectic world, it's getting increasing truly matters.
This is just a commercial tool that is working.
But now someone can help.
That can be working at home, in which we incorporate image recognition, face recognition of the users. They have an expert system implemented in this funny pillow tool that has information about all the members of the family, about the activity developed by all the members of the family, the possible, if medication is needed, which kind of medication they need, depending on the particular situation, the particular day.
Pilo, how many calories
and
in a celery stick?
maybe the problem of this ad is that this family seem very healthy and they don't need so much pills, but okay. I think they are actors and they do it very well. Okay. I'm just stopping here. But for instance, even in this case, this is an old guy that may have memory problems, and the machine recognizes his face, the moment of the day. It suggests which kind of medication, and in case it doesn't take the medication, it automatically calls, in this case, the son of the guy, to let him know that he's not taking the pill. So I mean,
as a true healthcare companion, and since he can sync with any wearable.
As Sergio said yesterday, we were promising that machine learning will work. We have been talking about that for many years, and the thing is that it's working. It's working now, and it's working, and some commercial applications are being developed in a routinely basis, and I hope that it will be also the case of quantum machine learning in the next few years. As I'm running out of time, in the last 2 points of my presentation, I just wanted to emphasize the mainstreams of quantum machine learning, which is basically what machine learning can do for quantum experimentation and the other way around, what quantum resources can do to improve learning. These are the two main aspects of most of your presentations. So this is why I've decided to bias my presentation a bit more to classical approaches to give you maybe a global idea of what is really being done in classical machine learning right now and the latest developments. So I will skip this a bit quicker. As I said, I want to again emphasize that active learning is something that I feel that will play a relevant role. And then I was thinking of talking about some of the wars in which I've been involved in the last few years, but lucky me, in this case, this will be explained on Friday, so I can skip it quickly. And some other recent quantum machine learning approaches in which I've been involved in the last few years, and in which I will be hopefully involved soon, and currently or in the next years. One of them is quantum clustering. Again, lucky me, Raul Casaña will explain it after the coffee break, so I can finish on time. So again, skipping this. I would like to talk a bit about that, but unfortunately I don't have time. And also quantum autoencoders that Lucas Lamata told me that he will talk about it on Friday, so I don't spend time here because I think I've already finished my time. Just to finish off, I think that in addition to all our current research, maybe we should think of, philosophically, of the concept of quantum learning, because there are some things that still need some research and some views there. For instance, with heard a lot of reinforcement learning here, and in reinforcement learning, as you say, we have the agent, we have the environment, and they are like kind of independent completely. They interact, but they are not the same thing. So, but what may happen in a quantum environment if they, for instance, become entangled? These are things that should be solved and should need special attention. And also, yesterday, Sergio said something about quantum deep learning. I think that is also one of the topics that should need special attention in the next few years. And just that, as I emphasize here in bold, after many years of research, Sergio said yesterday, we were promising that we will work in the future, this will work, now it's working. So after many years of research, now classical machine learning is a mature field of research that is really applicable in many different fields. And why not? Quantum machine learning may play a similar role in the next few years. So we should come up with something brilliant to achieve that goal. And there are also some topics here that are very popular to talk about them, but there are we still need special efforts to really achieve this real quantum supremacy. And one thing that personally I'm thinking, I don't ask me the solution or the answer because I don't know that, but I think that maybe we should come up with some proposals of not having like different realms, like the classical machine learning, the quantum one, and thinking of, okay, what can this classical do for quantum and the other way around, but maybe think of something holistic, something unified. It's something, again, a bit philosophical that I like to think, but I don't have the answer yet. If you have, please tell me now in the minutes of questions. And that's all. Thanks for your attention.
So thanks, Jose, for the great talk. Anyone have any questions for Jose? Thanks, Alexei.
Hey, could you, first of all, thank you for your nice talk, and I have a couple of questions. The first is, could you explain a bit more about how quantum machine learning can help in the work with small data? And the second one is how it's possible when we use generative and adversary networks, how it's possible to avoid cheating and batching. Because of, could you explain it a bit? Because of I didn't understand that.
Okay, in the case of small data, the thing is that actually is the usual situation in many problems. For instance, imagine, just to give you an example, that you are working for a hospital or maybe for a regional healthcare system. I mean, not a large company or a multinational company. Then you may have, if you are focused on a particular sickness, let's say, I don't know, people with cardiovascular problems, maybe your population is about 5,000 patients, and then you are only recording 20 samples, 20 features. So with this kind of data set, you have a matrix that, we call small data. It's not that we have just 10 records. Sorry, I didn't hear you.
How machine learning can help to work with small data, not what is small data?
How can help? Machine learning, historically.
Quantum machine learning. Yeah.
Quantum machine learning, okay. In the case of I give you an example that in which I was particularly involved recently. It was a problem in which we should send information, quantum information, in a quantum environment. Then in this case, it wasn't cheap to produce the data set. It's not cheap to produce a quantum environment with many particles involved. And in this particular case, you need, actually, you can't work with big data. I mean, the thing is that with quantum machine learning, with machine learning in general, but in the particular case of quantum machine learning, is not yet designed to provide solutions for big data problems. So, I mean, I think that, in fact, the scenario or the natural framework for quantum machine learning, for the time being, is to work with small data. Particularly, I don't know and I don't see how, at some point in the future, it will be able to work with big data as well. I don't see it right now, to be honest. But, I mean, it's a question that is the natural way of working with that. I mean, in both aspects, in the aspect of quantum resources to maybe improve a classical machine learning algorithm, that we've seen many examples in the last 2 days, or the other way around. For instance, that we have a classical machine learning that tries to model a particular quantum experimentation. But in both cases, for the time being, we are always in the case of small data.
Okay, cool. Thank you, Jose. Seth?
Well, I agree that it's very small data because we don't even have devices that are doing it at all. Okay? We have the systems that are doing machine learning right now are uses of the D-Wave machine to make small Boltzmann networks with Boltzmann machines with a few thousand nodes in it. However, I think that in the future, particularly if you look at recurrent and convolutional uses of quantum devices, the devices themselves don't have to be that large and have to have that much weights, but you can get quite a lot of data in. And just to give an example, if I have an ion trap quantum computer, and the clock speed of these computers is about 30 kilohertz right now. There's a new development from Oxford for it being a megahertz. So they're very slow, okay? But you address them optically, so you can put in light that if you put in data at something like telecom rates or faster, you could put it at 10 to the 14 hertz. So you can actually get in on the order of 10 to the 9th bits per clock cycle of this ion trap. And if you were, so you can imagine keeping on putting in data at a very fast rate, at the same rate or faster than you can actually put it into a conventional silicon-based neural network. So I don't think that, actually, I agree with you that at the moment the applications for quantum machine learning are very small data, teeny-weeny data, because of the teeny-weeny nature of quantum computers. But for the future, I don't think that, in fact, for the near future, I don't think that we actually have to limit ourselves to applications that require small data, particularly in the case where we're looking at things like recurrent or convolutional quantum.
Yeah, I agree with you. And a good aspect there is that we will be in a very nice situation for us as researchers of either even classical, but especially quantum machine learning, because as you say, maybe we will have very rich data sets with lots of information, but this information will be, I mean, well structured. I mean, it's not this kind of information that we have in social networks that it's short of rubbish and we have to do something with that. So the good thing is that we have a lot of information, which is our paradise as data scientists, but at the same time, we don't have so many artifacts as we have in other kind of classical data. So yeah, I agree with you, and I think it's a desired and a good situation to really extract knowledge in years to come. Yeah.
Thank you so much, Jose. I think there's a lot of room for discussion, so maybe we go to the coffee break and you guys can ask
Okay,
Jose,
thank you.
because we're actually running 10 minutes over time. So let's thank Jose again.